Okay, Module 14 is all about carbocations. You've seen carbocations before. They've shown up in earlier modules. And up to now, we haven't really explained why these weird things exist because we've really said that one of our most important rules for structures and whether or not they're stable is whether they follow the octet rule. So here's some examples of carbocations that you've seen before. These first couple come from Module 1. This one was in Module 6. This one over here was in Module 11. So you've seen these show up in various places, but they're not particularly stable molecules. In fact, every carbocation is inherently unstable. Think for a moment about why that is. And hopefully you've identified the key problem with a carbocation is that they all have an incomplete octet. You can see these two explicitly. They have 3 bonds, no lone pair, so they have an incomplete octet. The skeletal structures, you realize here, there is an implied hydrogen, but only one implied hydrogen. And then on this carbocation down here, there's no implied hydrogen. So again, they're making 3 bonds. They don't have a lone pair. So they have an incomplete octet, which means they've got space to make more bonds. And if there's one thing we know about electrons, it's that they love to be shared. Excuse me. And so when an atom has an empty orbital and space for making more bonds, electrons are going to want to fill that. So because they're unstable, I mean, we've drawn these, but we've always said they're unstable. So when do they exist? You'll never have a bottle full of carbocations because of that instability. We're likely to see carbocations only as reactive intermediates. That's a term we haven't necessarily used before, but an intermediate is a molecule or ion, a species that gets formed in the middle of a reaction. Because carbocations are unstable, they get formed and then very rapidly react in subsequent steps of the reaction. So they're produced in an early step of a reaction. And then they rapidly bond with something to complete the reaction. And we'll talk in a little bit about what those reaction steps are that might form a carbocation. But first, we're just going to talk about their structure a little bit. So whenever we encounter things, we like to think about their hybridization. So if I look at my pictures of carbocations, they're bonded to 3 atoms with no lone pairs. So think about that for a moment. What hybridization does that lead us to? They're going to be sp2 hybridized because they've got 3 electron domains. So if I want to think about how to draw a model of a carbocation, I mean, it's trigonal planar. So since it's planar, I could just draw it flat on the page. That's one way to draw it. And in, a reaction mechanism, we might just draw it that way. When we want to think a little more deeply about its structure, then we would probably tilt our perspective. So instead of drawing the carbocation flat on the page, I might draw the carbon in the middle and have 1 bond in the plane of the page, and then have my 2 other bonds coming into and out of the page, so that my trigonal plane has now been tilted 90 degrees, so it's perpendicular to the plane of the page. And that's going to allow me to think about, well, what's left over if it only has 3 electron domains, but it doesn't have anything filling that 4th orbital. It's going to have an empty orbital. And so if I have 3 sigma bonds, those sigma bonds are all going to be made by the sp2 hybrid orbitals. What's left over is going to be an empty p orbital. And that's going to be a defining characteristic of every carbocation, is it's got a vacant p orbital. And you can think of that vacant p orbital as being a huge invitation for other electrons to come get shared with that carbon. So other electrons see a vacant p orbital and they're like, oh, that is a chance for me to get shared. And electrons would love to be between 2 nuclei if they can. So they want to get shared there. So if we think about, all carbocations are unstable, but some are going to be less unstable. It's a little awkward. It feels like a double negative because throughout this discussion, I'm going to use the term less unstable rather than more stable, just to emphasize the fact that carbocations are all unstable, but some are more unstable or less unstable than others. So if we think about what might make one carbocation less unstable than another, the key factor is what other electrons are around that might get somewhat shared with that vacant p orbital and sort of ease the instability. So if there are other electrons around that can get donated, to the empty p orbital, that's going to be a stabilizing factor for any carbocation. And so that's what we're going to focus on when we think about how to compare one potential carbocation to another potential carbocation. This is a tool that hasn't been in our toolbox yet, because up to now we've basically said, well, if 2 molecules, if they're breaking the octet rule, we don't have a way to distinguish between 2 molecules that are both breaking the octet rule in terms of which one is more unstable or less unstable. Now we're going to introduce some ideas for how to do that. So here's an example. Here's 3 carbocations, and the one on the left is the most unstable, and the one on the right is the least unstable. So think for a minute about why that might be the case. Try and come up with some sort of explanation for why the one with the alkene next door is more stable than the one with just an alkyl group next door. And the one with the nitrogen next door is even less unstable than the one with the alkene next door. I'm going to pause, give you a minute to think about that, and then we'll resume. All right, I'm hoping during that pause you were able to come up with some ideas. We said that a carbocation's instability is really caused by the fact that it has that empty p orbital. It's ready to make more bonds, and having electrons nearby that could be shared with it would be helpful. So if you look at the middle molecule here with the alkene, note that the alkene electrons can get shared with the carbocation to make an alternate resonance structure. In that alternate resonance structure, we still have an incomplete octet. But that burden of the incomplete octet is being shared between two atoms instead of being just stuck on one atom. So having the pi electrons next door is a stabilizing effect on the carbocation. So that explains why that center one would be more stable than the one on the left, where there's no pi electrons next door to be shared. If we want to describe this in terms of donor and acceptor orbitals, we could say that the pi cc orbital donates to the empty p orbital on carbon. All right, and that's going to be a stabilizing effect. What about the one on the right? Well, if we think about what electrons are available there, in this case, we now have a lone pair next door that can be shared with the carbocation. Again, that makes an alternate resonance structure. In this alternate resonance structure, there's no incomplete octet. It actually follows the octet rule. So it's not a big leap to say, well, if we have an alternate resonance structure that now follows the octet rule, that's going to be a much more stable structure. And so we would expect that carbocation to be more stable. And in fact, this sort of carbocation we wouldn't even think of as a carbocation because the primary resonance structure, the most important one, is the one that follows the octet rule. So this is what the structure most resembles. So we can describe it in terms of resonance. We also might want to describe it in terms of donor and acceptor orbitals. In this case, it's a lone pair on nitrogen that's donating to the empty p orbital on carbon. From a molecular orbital standpoint, if we ask ourselves which is a better donor, pi cc or a lone pair is a higher energy orbital, so the lone pair is a better donor. So it has a greater stabilizing effect. So I think this discussion is really one that you could have understood after the very first module, where we just introduced the rules about following the octet rule and minimizing formal charge. If we can follow the octet rule, that's going to be better than not following the octet rule. Things get a little more, just to summarize the conclusion there. Having a good donor orbital next door helps to relieve some of that stress, and that has a stable, excuse me, and that has a stabilizing effect on the carbocation. Again, it doesn't make the carbocation stable, but it makes it less unstable. Things are a little more complicated, though, if we consider what about situations where there is no pi bond next door or no lone pair next door. Turns out we still see differences even when the neighboring groups don't have lone pairs or pi bonds. So on this slide, I'm comparing a methyl carbocation versus a primary meaning bonded to one other carbon. Secondary being bonded to two other carbons, tertiary being bonded to three other carbons. And it turns out, again, the methyl is the most unstable, and the tertiary would be the least unstable. of these in this group. So it turns out having those carbons next door somehow makes the carbocation less unstable. Um, so we have to explain that. And in this case, we don't really have resonance to fall back on. We're going to need to introduce a new phenomenon. So I'm going to draw again my carbocation. I've got my empty p orbital. So I've drawn it from the perspective where the plane of the carbocation is perpendicular to the plane of the paper, or the screen in this case. And now I ask myself, is there an orbital next door that could donate into this empty p orbital? And it turns out that there is. In this case, it would be the sigma CH orbital that's on that neighboring carbon. At any point in time, that neighboring carbon's tetrahedral, so at any point in time, one of those three CH bonds can align itself with the empty p orbital. So in this case, I've drawn one of them aligned up here on top. And so we can have some electron donation from the sigma CH orbital into the empty p orbital. This is related to resonance. It's not quite resonance. So we give it a different name. Resonance we generally consider when a lone pair or a pi bond is being shared with a vacant orbital. But in this case, it's what we call hyperconjugation. So in hyperconjugation, we have a sigma bonding orbital. That's what defines hyperconjugation. We have a sigma bonding orbital that's donating electron density to an empty orbital. In this case, the empty p orbital on the carbocation. So it turns out that has something of a stabilizing effect. Now, is a sigma bond as good a donor as, say, a lone pair or a pi bond? No, sigma bond is a worse donor. So this doesn't have as large an effect as resonance does. So it's important to note that this is a weaker effect than resonance, because sigma orbitals is not a great donor. But it still does have some effect. And it turns out if I have more than one carbon next door, so if I have a secondary carbocation, that additional carbon offers more opportunities for hyperconjugation, which has more of a stabilizing effect. Tertiary has three carbons next door, so at any point in time, you can have three of these sigma bonds. They could be sigma CC bonds or sigma CH bonds. You could have three of those bonds donating. So when you have more substituents next door, that leads to more hyperconjugation. More hyperconjugation means less unstable. As I mentioned, in the case at the bottom of the page, here I have a primary carbocation. So it can have sigma CH donate to the empty p orbital, just like I've drawn up above. If I consider the case on the right, though, this is a case where we actually have resonance. So in this case, what can donate to my empty p orbital is my lone pair on oxygen. My lone pair on oxygen can line up and make a pi bond. And so that is going to be a more effective donation, right? Here I could even draw it as an alternate resonance structure. So definitely this one on the right is going to be less unstable, because the lone pair is going to be a much better donor and have a greater stabilizing effect. So hyperconjugation is good. It's not nearly as good as resonance, but it does provide some stabilization. What we're going to find is that essentially methyl carbocations basically never happen. Primary carbocations will happen very rarely. Secondary will happen from time to time. And then tertiary carbocations are going to be much more common for us to see. But you'll see that as you do reaction mechanisms in the upcoming modules. You'll see that distinction between carbocations. I'm going to pause there, and then I'll pick it up and talk about how we actually form carbocations. When are you likely to see them? With the question of what situations would we see carbocations in? When will they actually show up? As I said before, they're generally reactive intermediates. They get formed in the middle of a reaction. Because they're so unstable, they pretty much immediately will find something to bond to. Right now, we're going to focus on just what that first step is like. And so two common situations where you'll see it happen. One is when you have an alkene and it reacts with an acid. All right, so if I have an alkene, I'll take ethylene, the most simple alkene, and I react it with an acid, so a source of H plus ions. That could be HCl or HBr or H2SO4. Some of those acids you dealt with in your Gen Chem class. If I have the pi bond go and attack the hydrogen, that's going to form a new bond to one of those two carbons. Which one to choose is kind of an arbitrary choice. I'm going to choose to bond it to the carbon on the right, so I'll highlight my new bond here. When I do that, I leave the carbon on the left with an incomplete octet and a positive charge. So alkene reacting with acid making a carbocation. There would then be a subsequent step that we'll talk about a little later. So that's situation one, where you're likely to see carbocations. Another situation where you will encounter carbocations is when you have, say, an alkyl halide with bromine or chlorine or iodine. Bromine and chlorine and iodine, those are what we call good leaving groups. We've seen that they're the conjugate bases of strong acids, which means they're pretty comfortable being on their own with a negative charge. And so when you have an alkyl halide like this, remember that even though we draw molecules on a page as if they're static, they're constantly moving around, they're constantly vibrating. And so every bond is vibrating. And depending on the temperature, there might be more kinetic energy, there might be less kinetic energy, but the more kinetic energy there is, the more likely it is that in some molecules, every now and then, one of those bonds will vibrate to the extreme, and you'll see this leaving group, this Br or I or Cl, just pop off on its own. Now, when it does that, remember the bromine starts with 3 lone pairs. It's now going to have 4. That bromine becomes negatively charged, and it leaves behind a carbocation. In the absence of any other reactants around, that bond would just reform. It would go back pretty rapidly to where it started. But if there are other reactants around, we might see some different outcomes. So this is another situation where you'll see carbocations getting formed where you have a halide in this case, Br, Cl, or I, act as what we call a leaving group. In modules 20 through 24, that's where you're going to see much more about those leaving groups and the reactions that they'll do. So those are the two situations. There are more, but those are the two that I want to start with for you to think about how carbocations might get formed. Now, if you have an asymmetric alkene, meaning you have an alkene where the two carbons are not equivalent, they're bonded to different things, then you have choices, right? I can draw one curved arrow. But that curved arrow is a little ambiguous because it doesn't tell me, am I going to bond the hydrogen to the carbon on the right, or am I going to bond the hydrogen to the carbon in the middle? And I get different results depending on which carbon I bond the hydrogen to. Based on our previous discussion, hopefully you recognize that my two choices here are not equivalent. I could have a tertiary carbocation, or I could have a primary carbocation. And hopefully you're starting to develop the intuition that, well, if I have a choice between these two, I'm going to form the one that's less unstable, or the more stable. So in this case, that would be the tertiary carbocation. So I would expect this one to be the one that gets made. And I don't expect to form any of the primary carbocation because that's going to be higher energy. It's going to be harder to form that one. This is an example of what we call regioselectivity. So notice my two products of this step are structural isomers. We call them regioisomers, where one atom or one group is bonded in a different place, in a different region of the molecule. And so this is called a regioselective reaction. The explanation is pretty simple. We already gave it. The tertiary carbocation is much more stable. And so it takes less energy to form. And it will be formed much faster. All right, I'm going to pause there, and then I'll come back and talk about some situations where this could be applied.